Swayam Prabha. Digital India. Educated India.
Hello everybody. Today I am starting module 7 and this is the lecture number 1 of this module. I want to discuss today the plate buckling using approximate method. There are different approximate methods available for the solution of the plate problem. In fact, any physical problem or mechanics problem can be handled by this approximate method. These are based on numerical techniques and the efficiency of the method can be improved by suitably selecting the method of integration or by taking sufficient number of terms in the assumed deflection. So, among the different methods, I am listing here the name of the 4 methods, but there may be other methods also. So, first method is Rayleigh-Ritz method, second method is Gallerkin's method, third method is finite difference method and the fourth is finite element method. The last one, finite element method, is not within the course prescribed here. So, therefore, I will discuss the first 3 methods in studying the buckling of thin plate. Okay. Now, you have some exposure in my earlier classes on the approximate method for plate bending, that is I discussed the Rayleigh-Ritz method, Gallerkin method and finite difference method for finding the deflection of the plate due to transverse loading and also the stress resultants. So, this method will be extended to study the buckling of the thin plate. So, you have seen the Rayleigh-Ritz method and Gallerkin method, these 2 methods that I am writing, 3 methods I have marked red, that means 3 methods I will cover in this course. So, first method you see Rayleigh-Ritz method and Gallerkin method, these 2 methods have their origins from energy principles. So, in Rayleigh-Ritz method we have taken the strain energy expressions and the work done by the external load on non-conservative forces, and then we use the variational method of this calculus and then we found the unknown coefficients of the deflected series. Okay. In the Gallerkin method, although the energy equation is not needed, but it has its origin from the virtual work principle. So, virtual work done by all the forces is 0 if the body or the system is in equilibrium. So, that is the principle, or in other words that we can also say that if the system is in equilibrium, the virtual work is 0. So, if the virtual work is 0, then we say that system is in equilibrium, but it can also be said in another way that for system is in equilibrium, the virtual work is 0. So, from that condition that we have found that equilibrium equation can be used in the virtual work principle, and then we derived a Gallerkin's equation that can be used with the assumed deflection function. In both the methods, the Rayleigh-Ritz method or Gallerkin method, we require to use the deflected surface of the plate, and deflected surface of the plate cannot be known or is not easily known by solving the equation or for complicated boundary condition that we encounter. So, therefore, we have to select an approximately deflected function that may consist of a polynomial or it may be a combination of polynomial and trigonometric series or it may be a combination of polynomial or hyperbolic function, or it may be a combination of hyperbolic and polynomial function. The choice of this assumed deflection function can be made in such a way that this function satisfy the geometrical and force boundary conditions at the edges of the plate. But sometimes it is difficult to satisfy both the conditions, geometric as well as force boundary condition. So, in that case we take a series which can at least satisfy the geometrical boundary condition, that will yield the result with reasonable accuracy. That has been observed in many cases, and that can be used for practical application also. The third method is finite difference method, that is another way of solving the plate problem using instead of this differential equation, we take the finite difference form of the deflection equation, and then we develop a number of simultaneous linear equation that can be solved to find the unknown deflection in the plate. Okay. So, let us discuss one by one. First, I will take up the Rayleigh-Ritz method, then I will take up the Gallerkin's method, and then finite difference method. Okay. So, Rayleigh-Ritz method has its origin on the variational principle, that you are seeing this equation, that is pi equal to u minus w, which is a very important equation, and that pi is capital pi is total potential. And what is this total potential? U minus w. U is the potential and strain energy of the plate in bending, and w is the work done by the forces. Now, here in the buckling problem, the work done due to transverse loading will be 0. That is, in buckling problem is a homogeneous problem. So, we neglect the transverse loading. Now, the work done will be evaluated based on the work that is done by the in plane forces. What are the in plane forces in the plate? This the nx, ny and nxy, that is applied at the edges. Okay. So, here is the difference, that work done due to in plane forces have to be first found out, and then it is algebraically added with the strain energy of the bending of the plate, and then we can find the total potential. Okay. Now, work done due to this membrane forces, that is nx, ny, nxy, that we can also term these forces as a membrane force, arises because of this in plane action. And when we calculate the work done due to membrane forces, we assume that this force does not change during the deformation of the plate. Now, here work done due to membrane forces that is involved in the expression W has to be calculated due to vertical displacement. The in plane strain, that is the direct strain arising due to in plane forces, is neglected in the small deflection theory of the plate, that is the Kirchhoff's hypothesis. So, therefore, we consider the work done due to membrane forces produced due to vertical displacement. So, that is the difference here. Okay. Now, according to variational principle, the variation of capital pi, that is total potential, equal to 0. So, this is the equation, that means we have to take the variation of pi. Pi contains the term strain energy expression and also work done by the membrane forces. Now, you can see that this pi contains the arbitrary constant that is assumed to form a deflection function approximately. Also, this W contains this arbitrary constant used to form the deflected surface. Okay. So, therefore, the strain energy term or work done, strain energy is a positive quantity. So, this strain energy term contains the square of this coefficient, and therefore, when we take the variation the square term reduced to linear term. So, that is the advantage of this variational principle, that we have to solve finally the linear equations to find the unknown coefficients. Okay. So, we assume that W x y equal to A 1 F 1 x y plus A 2 F 2 x y plus A 3 F 3 x y, in general A n F n x y. So, these are the terms that is taken to form the deflected series. Okay. Now, this coefficient is arbitrary, we do not know the magnitude. Sometimes when the accuracy is compromised, that is just a rough approximation is required, we can only take the first term. In some cases, for example, in simply supported cases, if we take the series as a double Fourier series, that is the Navier series, double trigonometrical series, then the first term will give very accurate result for the deflected surface, and higher number of terms are required to find out or to improve the accuracy in the bending moment and shearing force expression. Now, here f 1 x y and f 2 x y etcetera are the arbitrary function. Okay. So, what is this function? This function may be a trigonometrical function, may be this algebraic or polynomial function, or may be a combination of this, or may be a combination of sine hyperbolic and this cos hyperbolic function with trigonometrical function. So, the combinations are possible for different type of function. This is taken to satisfy the boundary condition. It has also to be bear in mind that if you choose a very complicated function, even it satisfies the boundary condition completely, the calculative effort, that means integration that is required in the variational principle finally will be very lengthy. So, even some authors, say Blasov has mentioned the eigenfunctions of the beam to form the approximate deflected surface of the plate for different boundary conditions. But in some cases the eigenfunctions of the beam are very complicated in nature. For simply supported beam, it is only a sine function, say sine n pi x by a L, L is the length of the beam. Now, in case of plate we take sine n pi x by a, that is one term. Then in the y direction also, if it is simply supported, y is equal to 0, y is equal to b, then we take sine n pi y by b. So, all these two functions actually satisfy completely the simply supported boundary conditions. So, eigenfunction for simply supported beam is a very simple in nature, but it is not so if I take a cantilever beam. So, for cantilever beam eigenfunctions are complicated, consisting of cos hyperbolic and sine hyperbolic function as well as trigonometrical function. How the eigenfunctions are found out, that is another question. Eigenfunctions are found out from the solution of the free vibration equation. So, free vibration of equation can be solved for different boundary condition to find out the eigenfunction, and that can be chosen as a trial function in the plate, that has been suggested by Blasov. But this method of taking eigenfunction in the plate problem requires a lengthy calculation, but it will yield the accurate result compared to some trial function that does not completely satisfy the boundary condition. Okay. So, let us discuss what is Rayleigh method. Suppose W x y is assumed with arbitrary constant a 1, a 2 etcetera, such that variation of this a 1, a 2 etcetera up to a n are arbitrary and non-zero. Then we can write this equation, variation of pi, that is the total potential, equal to differential coefficient of pi with respect to a 1 into delta A1, delta is the variation of symbol delta A1 plus del pi by del A2 into delta A2 plus and up to nth term if we take del pi by del an delta n. Actually, in the practical computation we have to take a finite number of terms. Although the Navier and Levy's method we have seen that summation contains the infinite number of terms, that is a infinite series, but practically the number of terms have to be truncated. So, therefore, you can take 3 terms, you can take 4 terms, 5 terms up to n, that is the finite number of terms you have to take. Okay. So, if I write this del pi using the partial differential coefficient, then we can take each of the derivative, that del pi by del A1, del pi by del A2 and del pi by del n equal to 0, because delta A1, delta A2 etcetera cannot be 0, and we have taken these are the arbitrary variation and non-zero quantity. So, therefore, delta pi, that is the variation of total potential 0, indicates that del pi by del n equal to 0, where n varies from 1 to up to n number of terms that we have taken. Okay. So, with this method now we can find the linear simultaneous equation containing A1, A2 etcetera, and we can solve it to know the complete deflected surface. Okay. So, in applying the Rayleigh-Ritz method, we must know the strain energy expression, that is U for the plate during bending, and if D is the flexural rigidity of the plate. What is the flexural rigidity of the plate? Flexural rigidity is related to the Young's modulus of elasticity, Poisson ratio and thickness of the plate. So, we can write that D equal to E h cube by 12 1 minus mu square, that is also possible. So, D is the flexural rigidity of the plate, and the expression for strain energy of the plate is derived earlier, and it is written here U equal to D by 2 integration 0 to A integration 0 to B del square W del x square whole square plus del square W del y square whole square plus 2 into mu del square W del x square into del square W del y square plus 2 into 1 minus mu del square W del x del y whole square and integration within the domain of the plate. Domain of the rectangular plate of size A and B is in the length direction from 0 to A, in the width direction 0 to B. So, we have substituted the limit of the integral as 0 to A for x and 0 to B for integration with respect to y. Okay. Now, adding a quantity 2 into del square W del x square into del square W del y square and subtracting the same quantity from this expression, we can arrange this expression in this form. So, del square W del x square plus del square W del y square whole square minus 2 into 1 minus mu into del square W del x square del square W del y square minus del square W del x del y whole square. Okay. Now, this quantity del square W del x square has the physical meaning that it is represents the curvature of the plate during bending. Okay. In the x direction. Similarly, curvature in the of the plate in bending due to y direction is del square W del y square. And what is this quantity? Del square W del x del y, that is the twist curvature. Okay. So, twist curvature is related to the twisting moment in the plate. Now, it is seen that the plate whose all edges are supported, support may be it is a clamp support, that is a fixed support, or it may be a simple support. So, when it is supported along all edges, then the term inside the parenthesis vanishes. Okay. That can be also observed. Now, you are familiar with this plate problem with this say Navier's method for rectangular plate. So, if you take a Navier series, So, for example, you take on the first term w is equal to say a sin pi x by a into sin pi y by b. Then substituting their second derivative here and multiplying them and subtracting this twist derivative square of the twist curvature from this quantity, you will get 0. So, this is also proved if the boundary conditions for rectangular plate whose all edges are supported, either clamped or simply supported, and has w equal to 0 and the slope along the normal direction to the boundary is 0. So, that quantity indicates that this strain energy expression where it is applied to circular plate, because circular plate boundary is curved. So, when we compute the slope for a curved edge, we have to take the normal direction and then del w by del n will represent the slope in the direction of normal to the boundary, and if these two quantities are 0, w 0 and del w by del n equal to 0, then strain energy expression will consist of only this term. So, strain energy expression in that case is simplified just like u is equal to d by 2 0 to a 0 to b del square w del x square plus del square w del y square whole square dx dy. Now, you can use either of this expression, even say you do not know, say this shape function is not very clearly defined, because in simply supported case it is clearly defined by Navier and it satisfies the boundary condition exactly. Now, in some cases when the shape function is not defined properly or not tested properly, then we can use the original expression also. There is no harm in using the original expression. Original expression is the general expression, and here you can see that del square w del x square whole square, that means if you assume a deflected surface, then this curvature square you have to integrate. You see the integration of each term, that means if you integrate this term, say this is integration part 1 I 1, then integration of this part will be I 2, the integration of del square w del x square del square w del y square 2 into mu will be third integral I 3, and then fourth integral del square w del x del y whole square double integration, and coefficient is 2 into 1 minus mu with respect to dx dy. So, you can integrate it in different components, say I 1, I 2, I 3, I 4, then you can add it. Sometimes it becomes convenient instead of squaring this quantity, because squaring of this quantity may lead you some complicated expression to integrate it, or it can be integrated, you will arrive at the same results, but the complexity arises because of the expansion of this quantity. So, the original expression can be taken in solving the problem, or you can take this expression after taking this term to be 0 for plate which has all edges simply supported or clamped, supported edges. So, either of this expression you can use. So, that is the strain energy due to bending, and that must be accounted for in calculating the total potential of the plate. Now, question arises, what will be the work done by the membrane forces? Now, since there is no external load applied for buckling, so due to vertical displacement of the plate, the work done by the membrane forces should be calculated. So, next task is to calculate the work done by membrane forces due to vertical displacement of the plate. So, we shall calculate the work done by each of the membrane forces n x, n y and n x y, and then we will add to find the total work done by the membrane forces due to vertical displacement of the plate. Now, let us consider the plate to be made up of a series of longitudinal strip. So, consider a plate, rectangular plate. In x direction we take a strip of width dy. So, in this strip, if the n x is the force along the x direction, then nx dy is the force on the strip in the x direction. Okay. Now, consider the deflected surface in the x direction. Okay. So, this shows the deflected surface in the x direction and the length of the element in the x direction is dx. Okay. So, in that case you can see that if w is the deflection here and at the end of the element the deflection will be w plus increment. What is the increment? If the slope is del w by del x, if this angle is del w by del x, then for small angle this angle multiplied by this distance, that is you can call it this say dx tan theta, but tan theta is here theta. So, we can write w plus del w by del x into dx. So, this is the deflection at this end. Okay. So, now we have to find the work done due to membrane forces nx dy on the strip. Okay. So, this work done dw1, I am denoting this here with dw1 is equal to nx dy, this is the force, and displacement, that is the change in position of the nx, will be ds minus dx. Okay. Because ds is the curved length and dx is the straight length. So, ds minus dx will indicate the deformation that is taken into account to calculate the work done by nx dy. Okay. Now, if I take ds as a small quantity, then we can form a right angular triangle. ds is the hypotenuse and dx is the base and dy is the altitude. From the right angular triangle we can write ds square equal to dx square plus dy square. So, naturally ds is now root over 1 plus del w by del x square into dx. dx is outside the square root. So, you can take this quantity. Okay. So, ds square is nothing but this the base of the right angular triangle, we take ds consisting of this side ds, dy and dx. Okay. So, ds square, that is the hypotenuse of the small right angular triangle, ds square equal to dx square, that is the base plus the height. So, height is del w by del x into dx, this distance. So, this square. So, this is giving you the ds square. So, ds is this that I have shown in my earlier slide also. Now, this expression can be expanded using the binomial series. Okay. So, this expression can be written as 1 plus del w by del x square to the power half into dx. Now, expand this using the binomial series or binomial theorem. So, provided the del w del x is less than 1. So, we can write it 1 plus half del w by del x whole square plus other terms, higher order terms will come. So, we will retain only these two terms because the deflection is small. Okay. So, therefore, dw1, that is the work done by the elementary force nx dy is now nx dy, and instead of ds minus dx we can now write this dy dx square into dx, half dy dx dy by del w by dx whole square, that we can write, that is the force, and half of this is the net displacement, because after subtracting this dx from ds we will get the net deformation that must be considered for calculating the work done by nx dy is half del w by del x whole square. So, we write the work done by the nx dy force on the strip of width dy as nx dy by 2 multiplied by del w by del x whole square into dx. Then total work done is nothing but the integration of this quantity within the domain of the plate. So, if it is a rectangular plate of side a plus b, then we can write the double integration 0 to a 0 to b nx by 2 del w by del x whole square dx dy. Okay. So, you have understood how the work done due to membrane force in x direction is calculated. So, similarly, the membrane force N y in the y direction can be calculated, and the expression for work done due to membrane force N y acting in the along the direction y on the edges, say y is equal to 0 and y is equal to b, can be calculated in this fashion. So, N y by 2 del w by del y square dx dy. This is calculated in the same way as we have done. So, instead of slope in the x direction, now we will consider for calculating the work done due to N y, we will consider the slope here this del y, okay, del w by del y. So, that quantity has to be considered, and then proceeding in the same way we can arrive the work done due to membrane forces N y is nothing but 0 to a 0 to b N y, this is the membrane force acting in the y direction per unit length divided by 2 into del w by del y whole square into dx dy. Okay. So, this represents the work done by the membrane forces N y. So far we have obtained the work done due to membrane forces W 1 and work done due to membrane forces W 2. Now, we want to calculate the work done due to membrane shear force N x y. Okay. Then we can add these three quantities of work done, and then can find the total potential completely. Okay. So, work done by membrane shearing force due to vertical displacement W. Okay. So, let us see how the shearing deformation takes place in a deflected plate, and how this deformation can be taken to consider the work done by the membrane forces. Okay. So, let us take two elements O A and O B. Here you are seeing that O A and O B, these are the straight element of the plate of small length, infinitesimal length dx dy. Dx is the length of the element in the x direction, dy is the length of the element in y direction of the plate, and then due to and let the plate undergoes the deformation just at the buckling point W, that is not the deformation due to external load or the transverse load. So, we can this is a small deflection of course, and let the line O A on O B takes the new position O 1 A 1 and O 1 B 1. So, these two position I have marked here. Okay. O 1 B 1 here, O 1 B 1 and O 1 A 1. Okay. This two position is the new position after undergoing the vertical displacement W. Okay. Now, the slope here along the x direction is del w by del x. So, naturally for small angle we can write this increment of deflection at this end is del w by del x into dx. Okay. Increment of deflection along the y direction, if del w by del y is the slope along the y direction, then we can write this the increment of deflection that b 1 b 2 is equal to del w del y into dy. Okay. We want to find the shear deformation, so that this can be accounted for in calculating the work done. So, difference of angle A 1 O 1 B 1 and the right angle, that is the pi by 2, is unit shear due to vertical displacement. Okay. That we know from our elementary strength of material. So, let us now proceed to calculate this what will be this angle. Okay. Let us rotate B 1 O 1 A 1 this angle, this plane, let us rotate this plane. This plane is formed after the deformation with respect to O 1 A 1. That means, taking this as the reference line, we rotate this plane. So, this plane is rotated by small angle del w by del y. So, that two planes B 1 A 1 and B 2 O1 A1 now coincides, and the point B2 is displaced to C. So, that is the that will actually your this shearing deformation will be now B1 C. Okay. So, we are now interested to find what will be the displacement B1 C. Okay. Now, if you see the displacement B2 C, this B2 C, for this angle that B2 C is inclined with the vertical line B1 B is nothing but the slope angle del W by del x, del W by del x. Okay. Now, for small deflection, this length of the vertical side is approximately equal to the length of the inclined side B2 C. So, the B1 C can be easily calculated knowing the vertical side B1 B2 and the angle between the vertical side and inclined side. Okay. So, then the side B2 C is inclined to the vertical. So, that angle is del W by del x is the slope in the x direction. Therefore, shear deformation due to vertical displacement W is now B1 C. So, what is B1 C? Because B2 C is now del W del y, del W by del y into dy. So, this vertical side is approximately equal to B2 C. Okay. So, B1 C1 is nothing but your say this B2 C into sin theta, theta is the small angle here, theta there is a small angle that is del W by del x. So, actually this B1 C now becomes, this is the length of the side B2 C and the angle sin theta equal to theta. So, this is the angle del W by del x. So, ultimately the shear deformation now becomes del W by del y into del W by del x into dy, del dy. Okay. So, hence the work done by the membrane shear force N y x acting along dx is nothing but N y x into del W del y, del W del x dx dy, and after integration over the domain we get the total work done by the membrane shear force. Okay. So, since N x y is equal to N y x, so there will be no difference when we write N y x or N x y. Total work done by the in plane forces or membrane forces now can be expressed in this form N x by 2 del W by del x whole square plus N y by 2 del W by del y whole square plus N x y del W del x del W del y and integration. You can note here this component is the work done due to membrane force or in plane force in the x direction due to vertical displacement, and this component is the work done due to membrane force in y direction due to vertical displacement of the plate, and this is the work done by the membrane force shearing force, membrane shearing force N x y or N y x due to vertical deformation. So, the vertical deformation introduces additional shear, that is del W by del x into del W by del y. So, this has been taken into account to find the work done, and it is also to be noted that during deformation this N x, N y, N x y does not change. Okay. So, now with the help of this we can now write the total potential capital pi. So, total potential capital phi for the buckling problem is now given as d by 2 integration 0 to a 0 to b, that is the curvature in the x direction square plus curvature in the y direction square plus 2 into mu, mu is the Poisson ratio del square W by del x square into del square W by del y square. So, 2 curvature product and then 2 plus 2 into 1 minus mu, this cross this twist curvature del square W del x del y whole square, and integration is done over the domain of the plate. So, red color term is the strain energy during bending of the plate, and blue color term is the work done due to membrane forces due to vertical displacement. So, work done of membrane forces when the plate is undergoing the vertical displacement, then this quantity is written as the work done for the membrane, and we take this total potential pi as u minus w. So, total potential has to be computed first in case of Rayleigh-Ritz method, then we can apply the method taking a suitable shape function. Okay. Let us illustrate this method with an example. Okay. So, I have taken an example of this plate which has this fixed edges. So, all the edges are fixed. So, this type of problem cannot be solved by using the Navier's method or the Levy's method. So, therefore, we take the help of approximate method. Okay. Now, here you can see the assumed deflection function. I have taken only the first term, other terms can also be written. Taking origin at O, I have taken this function, the function of x, that is 1 minus cos 2 pi x by a, and this function as a function of y, 1 minus cos 2 pi y by b. It is easily verified that these two functions satisfy the condition of clamped edges. That is, what are the condition of clamped edges? Two conditions at the clamped edges should be present. One condition is deflection is 0 at the clamped edge, another condition is slope along the normal direction is 0 at the clamped edge. So, if I calculate the deflection at x is equal to 0 edge, x is equal to 0 edge is this edge, you can see that w is 0, because when you substitute x is equal to 0, this factor becomes 1, cos 2 pi x by a becomes 1 and 1 minus 1 is 0. So, naturally w is 0. If I calculate the slope at x is equal to 0, then del w by del x will be this sine function will come. So, a will be there, and here you will get sine 2 pi x by 2 pi x by a, and another factor will be there because of differentiation, 2 pi by a will be there. So, this will be constant. So, the slope, that is the first derivative, again at x is equal to 0, because sine 0 is 0. So, therefore, the slope and deflection both are satisfied. This is also verified at x is equal to a edge. If you substitute here x is equal to a, then cos 2 pi is again 1. So, deflection is 0, and when again you differentiate it for finding the slope, then sine 2 pi x by a term is appearing, and when x is equal to a, again sine of 2 pi, that is sine of any integral value of pi is 0. So, therefore, slope 0 is condition is satisfied at x is equal to a edge. Okay. Similarly, y is equal to 0 and y is equal to b, these two condition w is equal to 0 and del w by del y is equal to 0 satisfied. So, this function adequately represent the deflected surface of the plate which has clamped edges along all the edges. So, strain energy of the plate can be written now, U is equal to d by 2, d is the flexural rigidity of the plate, 0 to a, 0 to b integration, then the curvature along the x direction square plus curvature along the y direction square plus 2 into mu del square w del x square del square w del y square plus 2 into 1 minus mu, and then del square w del x del y square dx dy. Okay. The plate is subjected to uniaxial compression. So, to calculate the work done by the membrane forces, only this component is pertinent. Other component of work done N y and N x y will be absent here, because these forces are not acting in the plate. So, plate is acted upon by only the uniaxial compression, and that compression is along the x direction. So, compression acts along the edge x is equal to 0 and x is equal to b a. Okay. So, work done due to this compressive force is now written like that, w is equal to integration 0 to a 0 to b n x by 2 del w by del x whole square dx dy. This expression has been derived earlier from the basic principle. So, you can use it. Okay. So, total potential is pi equal to u minus w, and that has to be now applied, or that has to be differentiated, actually differentiated with respect to the constant that is used to find the deflected series. Okay. Now, since del A are the non-zero parameters, so we differentiate this to find this. Actually, we want to find the arbitrary variation of pi. So, we can write delta pi equal to del pi by del A into dA. Now, since the deflection is a function of only one variable, we can write it as ordinary differential coefficient also instead of partial differential coefficient. Okay. So, now we can see that the strain energy expression that has to be computed first, and it contains the second derivative of the w. W is this, the assumed deflection function, as well as the cross derivative of this function, that is the mixed derivative. So, these derivative are calculated, and this you can see del w by del x, you can easily see 2 pi by a will be there, and a cos 2 pi x by a 1 minus cos 2 pi y by b. Okay. Then your this function del square w del x square will be this type, again this differentiating this. Similarly, del w by del y will be like that, and del square w del y square will also be written like that, and this integral are also useful. Okay. This integral are useful, sin square 2 pi x by a dx equal to a by 2 due to orthogonality condition of the function, and also the cos square 2 pi x by a dx equal to a by 2 due to orthogonality function of the orthogonality condition of the shape function, and this function is integration when this function cos 2 pi x by a is integrated between the limit 0 to a gives you 0 value. So, results for a square plate. Now, let us use this result for a square plate taking a is equal to b. Okay. So, strain energy expression now can be found out by putting the integral individually. You can see here the integral. If I see this is the first part of integral, this is the second part of integral, this is the third part of integral, and this is the fourth part of integral. So, all these derivatives are calculated, and after calculating this, then we integrate it, because this will be a function of sine and cosine, and sometimes the orthogonality condition is used very easily. So, you will find that integration in 4 parts are calculated, 4 components are calculated. This integral represents this first component del square w del x square whole square, and this is also same because it is a square plate. So, curvature in both the directions are equal. So, therefore, you will get this again for the square plate, this integral, and then product of these two del square w del x square del square w del y square, when this is integrated product of the curvature is integrated, and here the square of the curvature is integrated. Note the difference, here you are integrating the square of the curvature, this is also the square of the curvature integrated yields you this result, but here product of the curvature is integrated. So, its result will be different, and this result is 2 into mu s square by 4. Then the mixed derivative, that is the twist curvature is squared up and integrated. This is the fourth component of the strain energy, and this gives you this quantity. Okay. So, after simplifying, you are getting that strain energy U equal to 16 d pi to the power 4 s square by capital S square. Capital A is the unknown coefficient of the deflected series that we have to find out, divided by small s square. Small a is the size of the plate, because we have taken a square plate whose side is a cross a instead of a cross b for a rectangular plate. Now, let us calculate the work done due to the membrane force, in plane force or direct force you can call it, direct compression, that is Nx. So, Nx is applied along the x direction, and we know that expression for the work done due to membrane force, this Nx is double integration 0 to a because this is a square plate, Nx by 2 into del w by del x whole square dx dy, because this represents the work done by membrane forces due to vertical displacement of the plate. So, calculating this derivative and then integrating, we can now see that integration becomes this, and after simplification we get this w is 3 Nx pi square a square by 2. So, two component of potential, total potential we have calculated. Now, we can form the total potential. So, total potential is formed pi equal to u minus w. So, you can write pi equal to, pi is the total potential equal to u minus w. When you form the total potential, then apply the Rayleigh-Ritz method, del pi by del a. Now, since the functions or the strain energy and the work done due to membrane force is found to contain only one variable, unknown variable that we want to deal with the variational method is a. So, therefore, we can write it simply a ordinary differential coefficient d by dA, and inside this we write here this strain energy expression that we have found minus this work done. So, after differentiating and then treating A should not be 0 for non trivial solution, then we get the critical value of the load as 32 d pi square by 3 a square. So, this is one method that by which you can calculate the strain energy of this buckling load of the plate, and here we have taken only one term in the series, but if you want to increase the accuracy of this series, accuracy of the result, then you can take more number of terms. Let us see what is Gallerkin method in plate problem. Plate problem, we have already used the Gallerkin method, which is again approximate method, but difference of Gallerkin method with Rayleigh-Ritz method is that Gallerkin method requires the differential equation of the plate, whether it is under bending or it is in buckling or even in the vibration problem. You require the governing differential equation instead of the strain energy expression. Although both the methods are derived from the work energy principle, but one method is directed in such a way that the first method that I discussed, Rayleigh-Ritz method, has to be started only after knowing the strain energy of the system and work done of the system. But if we see the Gallerkin method, then instead of strain energy, we start the calculation by knowing the differential equation of the system. So, here the system is the plate and it is under buckling. So, therefore, the equation for buckling of the thin plate is taken in presence of all the membrane forces which are treated as constant, but if these are not constant, then this Nx, Ny, Nxy will be function of xy. Okay. Now, define a operator L such that L is del 4 plus Nx by d del square del x square plus Ny by d del square del y square plus 2 Nxy by d del square del x del y. So, introducing this operator, we can now represent the differential equation in this form. So, Lw is 0. So, L is a operator I have introduced. You can isolate W from this equation and then you will be able to get the operator. Okay. Now, in the Gallerkin approach, again we require to choose the shape function. So, shape function is chosen in the same way that we have carried out in case of Rayleigh-Ritz method. So, shape function is chosen such that it satisfies the geometrical and force boundary condition. There is the most important part, and the choice of function in a judicious way will reduce the calculative effort and also improve the accuracy of the result. So, therefore, this is the very important step in carrying out or solving the problem by Rayleigh-Ritz method or Gallerkin method to choose a suitable shape function. Okay. Now, here again we write the shape function in the form of a series. Series means f x y may be a function, say f 1 x y may be some trigonometric function, and then f 2 x y may be another trigonometric function. So, adding all these things we get this the total deflected shape. Now, here you can see that individually f 1, f 2, f 3 etcetera should satisfy the boundary condition of the plate. Now, boundary condition here I mean that geometrical boundary condition or the force boundary condition. Sometimes geometrical boundary condition is very easily satisfied and force boundary condition is difficult to satisfy at all, sometimes partly satisfied. But in any way, when the geometrical boundary condition is satisfied, we take this deflection function to be used in the Gallerkin approach or Rayleigh-Ritz method. The criteria for selection of shape function in Gallerkin method and Rayleigh-Ritz method both are same. So, after choosing this shape function, then we form the Gallerkin equation like that. This is the differential equation into f n x y dx dy equal to 0, which is integrated in the domain of the rectangular plate. Now, here you can see the shape function is approximate, that we take sometimes we get it exactly choose it exact function sometimes. Say for example, in simply supported plate along all edges we take the Navier's series, then it represents the exact deflected shape. So, therefore, the function is exact. So, but in general the shape function is not exact and it is approximation of the deflected surface. So, when you substitute the approximate deflected surface in the differential equation, the right hand side you will not get 0. So, therefore, it represents an error, a non-zero quantity which represents error. This may be small or this may be large depending on the choice of the shape function. Now, when this error you can see after substituting w in the differential equation, this L w represents the operator L into w, L w represents the error introduced due to assumed deflection function. So, the error multiplied by each of the function taken to form the deflected surface is integrated with respect to x and y between the limits 0 to a and 0 to b and equated to 0. So, this is the Gallerkin equation that has been derived from the first principle, virtual work principle. Okay. Now, here we take a problem of plate under pure shear. Okay. So, this pure shear case is commonly seen in case of this plate girder, say web of a plate girder. For example, this is the web of a plate girder, a portion of a panel of a plate girder, web panel of a plate girder. Now, you can see that due to the shear acting on the element panel, you can see diagonally it is compressed, but in the other diagonal there is a tension, and this tension sometimes reduces the or minimizes the chance of buckling failure, but due to compression here there is a chance that shear buckling may takes place in the panel. So, the shear buckling phenomenon is observed in many practical cases. This is one photograph of a plate used in the ship construction, and you can see due to diagonal compression that the buckling takes place due to compression. So, that is practically observed. Therefore, the study of buckling of plate due to in plane shear is also important, significant, and here you can see that in plane forces n x y is applied, and we take A is equal to B, that is a square plate, okay, to simplify the calculation. All right. Now, we take the function, the shape function as consisting of two terms of the Navier series, because we taken the support as a simply supported. So, we take the support as simply supported, and therefore, we take this shape function as consisting of the two terms of the Navier series. So, a 1 sin pi x by a sin pi y by b a plus a 2 sin 2 pi x by a into sin 2 pi y by a. Okay. Now, in Gallerkin method, we take the differential equation that I have introduced earlier, and this differential equation now has to be satisfied by this approximate function. So, therefore, naturally a error will be introduced. So, this error what is there will remain here, and then this error multiplied by each of the functions. So, what are the functions are taken sin pi x by a into sin pi y by a. So, this is one function f 1, and f 2 is plus a 2 sin 2 pi x by a into sin 2 pi y by a. So, this is L w into f 1 x y equal to 0 and L w f 2 x y equal to 0, because two constants are involved in forming the deflected shape. So, therefore, two Gallerkin equations are written. Okay. We take the square plate. So, in all places we substitute b with a. Okay. So, this integral are important to be used here, and after carrying out this integration you will finally arrive two homogeneous equations in a 1 a 2. This is a homogeneous equation in a 1 a 2 is a linear equations. Okay. So, one possibility is that a 1 equal to 0, a 2 equal to 0, then this equation two equations are satisfied, but this condition will not give you the result that we required for this buckling load. So, this will form a trivial solution with a 1 equal to a 2, a 1 and a 2 being 0. So, this solution we discard. For non-trivial solution, we take the determinant formed by the coefficient of this equation to be 0. So, determinant formed by the coefficient of this equation, say this coefficient with a 1 will be in the first row first column of the determinant, pi to the power 4 a to the power a square. So, this is pi to the power 4 a square. Then second coefficient in the first row, that is the second column of first row, 32 n x y 9d. So, this is then this from the second equation we picked up this coefficient in the first column second row, and this term we pick up for second row second column. So, expanding the determinant and equating to 0, we get now the value of n x y. So, n x y is this root over this 16 pi to the power 8 a to the power 4 into 81 d square by 32 square. So, that is under root, and after calculating we get the critical membrane shear which cause the shear buckling in the square plate is 11.103 d pi square by a square. Okay. So, let me summarize the topics that I have covered today's lecture. So, in this lecture the buckling of thin plate by two approximate method, Rayleigh-Ritz and Gallerkin's method have been discussed. So, formulations were carried out using the membrane this work done due to membrane forces, or you can tell it the potential of the membrane forces. Then Gallerkin method is also shown how it is evolved with the help of differential equations, and both the methods have its origin from the work energy principle, that we have to bear in mind. The work done by the membrane forces has been derived from the first principle, and work done and strain energy expressions are specifically required for Rayleigh-Ritz method. In Gallerkin method, you only need the differential equation, and then your this of course, your assumed shape function that are same in case of Rayleigh-Ritz and Gallerkin method. So, two examples have been solved for a rectangular plate using these two methods. Okay. So, thank you very much.